Hello students, welcome to the lecture series by Center for Distance and Online Education, Bharati Vidyapeeth, deemed to be University Pune. I am Dr. Suvarna Patil. I am the facilitator for the subject Operating System for BCA course. So let's start. In this video, we'll be discussing about the unit storage management. In this unit, we'll discuss all these points one by one. Let us see the introduction. Let us see what is the meaning of storage management. Now you take any system, the main objective of a system is to execute the program. The purpose of any system is to execute the program. Now these program and data must be loaded in main memory when they are in execution. So here primary memory we are using for loading all this data and the program in the memory. It is a very small in size to accommodate all the programs permanently. The computer system uses a secondary storage to back up the main memory. To increase the productivity of system resources, the computer system loads many processes in memory. Now to load multiple numbers of program in memory, the memory management is required. Basically, we have less amount of memory and we want to execute more programs, more process in the memory. So here we need to manage the memory. So memory management is required. Operating system does the following activities. It keeps track of used and unused memory. It decides which processes will be swapped in and out of the memory, and it does the allocation and deallocation of memory space. So this is the purpose of memory management, storage management. Let's see basics of memory management. There are three important memory management issues. One is relocation, then protection, then sharing. Now, relocation, what it means? A program may be relocated in the memory, may be due to swapping of the processes. So, while the process is executing in the memory, the relocation may be required. Relocation means the process will change the addresses when they are executing in the memory. So next time when we will take the process for execution, the process may not get the same area, same space in the memory. It may get relocated. The next issue is about protection. Now process will not use a data of any other process without the permission. So here process is allowed to use its own data, own resources, and it is not allowed to use a data of any other process without its permission. So through memory management, we should provide the protection to all processes. Sharing. Operating system, it permits the process to access a common portion of memory containing data or program with proper protection mechanism. So here we will share some memory within the processes. So sharing will be the one more issue that should be handled under the memory management. We see what types of memory management we may need. Monoprogramming without swapping and without paging. So here the mechanism, it loads one program at a time in the memory for execution. As you can see in the diagram, on the upper side we have a user program. On the lower side, operating system is loaded in the memory. So this can be one scenario of your OS, of your memory, how it is occupied by operating system and user program. In the second scenario, you can see operating system can occupy the upper part of the memory and user program may be in the lower part. In the third scenario, we can divide the portion. The device drivers may come in the upper part. The user program will occupy the part in between, and at the lower side we can load the operating system inside the memory. So here relocation will not be an issue because user program is loaded into the same memory location at one time. So here MS-DOS operating system falls in this category. So operating system may be loaded at the bottom of RAM, or it can be loaded on the upper side inside the memory. So any scenario, any situation may be there in your own operating system. So it's regarding monoprogramming without swapping, without paging. As opposed to monoprogramming, we have multiprogramming with fixed partition. So here we'll divide the memory into fixed number of unequal partitions. When the process will enter in the system, it will put in the input queue for the partition that is large enough to hold it. So in this A diagram, we can see the operating system is loaded on the lower side, and the upper area, it is divided into 4 partitions with unequal size. In this B diagram also we can see operating system is on the lower side and the upper side of the memory is divided into 4 partitions of unequal size. Now here for A diagram we can see multiple input queues are maintained. So for each partition we have separate queue. Now when we have a separate input queue for each partition, at some partition you can see many processes are waiting, whereas for some partition there is no any process waiting. So here it will give to rise to wastage of some memory. Now when we have a single input queue, it is common single input queue which is maintained for all partitions. Now when the partition becomes free, the processes at the front of queue is loaded into the empty partition which is enough to hold the process and execute. Now here drawback of this single input queue technique is it is inefficient to use the memory because of the internal fragmentation. Here what will happen, some process will occupy the partition and there will be some part of the memory which will be wasted inside the partition. So the single input queue technique will face this problem of internal fragmentation. So that is a wastage of some part of the memory. Let's talk about the addresses which are used by the operating system. Address is uniquely identifying a location in the memory. Logical address. The logical address is basically a virtual address. It is generated by CPU during the program execution. So it's basically a virtual that does not exist physically. This address is used as a reference to access the physical memory location. Now here set of all logical addresses generated by the program, they are called as a logical address space. Now when the CPU program generates a logical address, it is mapped to the corresponding physical address by the hardware which is called as a memory mapping unit. What is physical address? It refers to the actual location in the memory unit. With this table, we can see the difference and the comparison between logical address and physical address. So basically, logical address, it is generated by CPU, it is a virtual address. And physical address, its actual location in the memory unit. Address space, the whole set of all logical addresses will be called as a logical address space, and set of all physical addresses will be called as a physical address space. What is visibility? Here the user can only view the logical address of the program. But regarding physical address, the user will never view the physical address of the program because it is used internally, used by the operating system. It is never visible to the programmer, never visible to the user. Access: the user uses the logical address to access the physical address. User cannot directly access the physical address. Who is generating this? The logical addresses is generated by the CPU, and the physical address, it is not generated, it is computed or converted by using the hardware called as a memory management unit, MMU. Let's see the next concept, swapping. Now in many systems, if enough memory is not available for the execution of the program, they are kept on the disk and they will be bought in to run dynamically. So what is swapping? Swapping is the memory management technique in which processes are moved in and out of the memory to create a room for new incoming process. So some processes are sent back to the disk. So basically it is in and out of a process from memory to disk. With some reason, if the enough memory is not available for new incoming process, then the idle process, suspended process, some of the processes can be selected and they will be swapped out of the memory and they will be sent back to the disk. Now here benefit of swapping is it will give you higher degree of multiprogramming because the idle process, suspended process, they are wasting the memory, they are unnecessary occupying the memory, so they can be sent back to the disk. Here dynamic relocation is possible. After some time when you are taking the process back in the memory, the relocation will be done. So for better memory utilization, one can go for a swapping. Operating system does swapping internally. In this diagram, we can see this A, we have operating system and process A. And this is unused area. After some time, B process will come in the memory. And this will occupy this space. So this dark area, shaded area, it's again an unused memory area. After some time, C will enter. This much space is given to the C process, and again this much dark area is unused memory area. After some time, A process has completed the task or it has been swapped out of the memory. So this partition, this area of the memory is again free. After some time, D will enter in the operating system and D needs this much amount of memory. So D can be loaded here. So D, free area, B, C, again some free area. After some time, B will be going out of the memory. It has completed the processing or it has been selected for swapping out of the memory. So B will go out. So this free area and B is now out. So this much area is again a free area in the memory. So D, free area, C, again some area is free. After some time, A is again decided to be executed in the memory. So A will again come in the memory. So here we have a scenario seen like we have D, A, C, three processes running in the memory and some part is again free in the memory. Now here fragmentation is one of the issue that can be faced in case of memory management. So it can be external fragmentation or it can be internal fragmentation. Now when the processes are loaded and removed from the memory, the free memory space is broken into little pieces. So it happens that after some time that process cannot be allocated to the memory block considering their small size and the memory block remains unused. So that thing is called as a fragmentation. So it's basically an unused memory area where we can't allocate that area to the process. Now, there are two types of fragmentation. We have external fragmentation, we have internal fragmentation. In case of external fragmentation, it is a total memory space which is enough to satisfy a request or to reside a process in it, but it is not contiguous. So it cannot be used. In internal fragmentation, it is the memory block assigned to a process and it is bigger. So when the process is small and the partition allocated to the process is big, in that case small portion of memory which is left unused, it cannot be again assigned to any other process. So that kind of fragmentation is called as a internal fragmentation. So basically fragmentation is wastage of memory, but in external fragmentation whole partition is free, but we can't assign that because the partitions are not contiguous. In internal fragmentation, it is the memory vested inside the partition, but it's again a small amount of memory. Now, in case of internal fragmentation, the problem can be solved by using a technique which is called as a compaction. So here multiple holes which are generated because of internal fragmentation, they are taken together, so they are combined together and they will form a big hole or big empty space, and that technique is called as a compaction. So internally operating system may using a technique of compaction, but compaction it will consume the lot of CPU cycles, so it is again taking your resources. So that is the case of internal fragmentation. We see how the memory can be managed. The memory can be managed using some techniques, that is memory management with a bitmap and memory management by using a linked list. Now here operating system keeps track of memory in two ways: with the help of bitmap. In bitmap, what it is doing, here the memory is divided into small allocation units. The size of allocation unit, it will vary from few words to several kilobytes. Now for each allocation unit, there is one bit in the bitmap table. If bitmap contains 0, allocation unit is free. If it contains 1, it means the allocation unit is occupied. It is not free. The size of bitmap table, it depends on the size of allocation unit. The smaller is the allocation unit, the larger will be the bitmap. And if larger is the allocation unit, smaller will be the bitmap. Now here bitmap, it is providing you a simple way to keep track of memory management, and easily we can identify how much memory is free and how much memory is occupied. Now here, if you see the diagram carefully, this is a bitmap table. Here the digits are either 1 or 0. So 0 means the memory is free and 1 means the memory is occupied. We can see there are contiguous 5, 1 in the bitmap table. They are denoting to the process A. So process A has occupied 5 allocation units in the memory. After that, you can see there are 3 zeros. Now these 3 zeros, they are indicating this area. So we have 3 allocation unit and those are free. They are unoccupied. Again after that, you can see multiple ones are there and they are for B and C. There are 2 zeros, it is for this free area. So in this way, this is your memory occupied and some is free, and which is denoted or displayed or represented with the help of this bitmap. It will have only numbers as 0 and 1. Now second technique for memory management is using a linked list. So with the help of linked list, we can manage the memory. Here you can see every node is containing some data. Now here the node is containing a letter as P and the node is containing a letter as H. Now P stands for process, H stands for whole. So if there is a process, that node will be indicated with P as a process. This second part will denote the starting and this third part will denote the length of that particular process. Now there are the nodes and they are linked with the help of pointers. So with the help of linked list, we can manage the memory. So here we can see in the memory we have first process and it is allocated 5 units and starting is 0. It is indicated as process. It's a process A basically. Starts with 0 and it needs 5 allocation unit. After that, this is a free area which is indicated with this particular node. It's a free area, so denoted with H as whole. The starting is 5 and it has 3 allocation unit, 1, 2, 3. So in this way we can represent the memory with the help of a linked list. Now when we want to allocate the partition or the memory for any process, this can be the scenario. It shows that we have a process A, X and B. After some time, X terminates. So here this area is now free, which is shown in the shaded area, dark area. This B scenario shows that we have A process, we have X and some empty space is there. Now after this, if X terminates, what will happen? We'll combine this X and this empty space into one single whole, one single partition. They are merged together, they are combined together. The next scenario in C, it shows that empty area, then we have X process, then we have B process. Now when X terminates, again these two empty partitions are combined, they are merged together into a single empty partition, single whole. And this last scenario, it is showing you we have empty space, then X process, again empty space. Now when this X will terminate, we'll have a big hole, big partition available for the allocation. So it shows 4 neighbor combination for the process X before X terminates and after X terminates. Now when you are allocating the memory for a new process, maybe it is swapped out and now you are swapping it in, we can use 4 technique for the allocation of the memory for the process. We can use first fit, next fit, best fit and worst fit. Now according to the first fit technique, what we can do for the new incoming process, we'll allocate the partition which is enough for the execution. So we'll not scan the whole list of the memory, will not scan the whole list of the partition. So the whole partition which is first available and enough to execute the process will allocate that whole, that partition. In the next fit technique, it will maintain the best possible partitions so that next time when the process will come, we can allocate that particular whole partition to the process. In best fit, it will exactly scan the whole list and only the required area of the memory will be allocated to the process. So in best fit, there will be less wastage of the memory. So according to the requirement of the process, only that much amount of area is allocated to the process in best fit. The last is worst fit. In worst fit, the process will get the whole which is big and we can easily execute the process. So here the perspective behind this worst fit is the process may increase at the time of execution. So as per worst fit, we have to allocate the whole which is big enough. So it is largest whole which can be allocated for the process. So it's about memory management using bitmap and the linked list. Let us see how the memory can be allocated. So memory is a large array of bytes. So where each byte has its own address. Now memory allocation, it can be contiguous or non-contiguous. Now in contiguous memory allocation, it will assign the consecutive blocks of memory to the process. As you can see here, we have 2 blue blocks, we have 3 green blocks, then we have 2 yellow blocks. So the continuous memory is allocated to the memory in contiguous memory allocation method. In non-contiguous memory allocation method, it assigns the separate memory block at different location in memory space. So here in non-contiguous memory allocation, it will reduce the memory wastage which can be caused due to internal and external fragmentation. This is the situation of non-contiguous memory allocation. One blue block is here, other blue block is here. So it is a non-contiguous memory allocation. On the right side, we can see the differences between contiguous memory allocation and non-contiguous memory allocation. As we have seen, it allocates the consecutive blocks in contiguous, and here separate blocks will be allocated to the process. In contiguous, it doesn't have an overhead for address translation, because if you know the starting address, we can know the ending address of the process, just like an array concept in C. But in non-contiguous, the overhead of address translation while execution of process will be required. In contiguous memory allocation, the process executes very fast because the blocks are contiguous. But here it may slow down the execution of a process. Here in contiguous, the space is divided into fixed sized partition. You can see here, this is the all sizes of the partitions are fixed. Here in non-contiguous, the process is divided into several blocks and they are placed into different parts of the memory according to the availability of memory space. So this partition is big, this is small, and this is also a big partition. In contiguous, a table is maintained by the operating system that maintains a list of available and occupied partition in the memory space. So just we have seen with the help of bitmap or any other technique, it will maintain a table for free area and occupied area. In case of non-contiguous, a table is maintained for each process which carries the base address of each block, and that has been acquired by the process and that will be used while execution of the process. So more headache and overhead is required in case of non-contiguous memory allocation, but that will reduce the internal and external fragmentation. The remaining part of this unit will be discussed in the next video.